Great. So let's get started for today. Okay, so let's get started for today. Today we're going to be talking about Bayesian Metalearning, and specifically we'll talk about what are the benefits of this class of approaches. We'll describe different ways to integrate kind of Bayesian graphical models into metalearning approaches, both for black box approaches and optimization-based approaches. And then finally, we'll talk about evaluation and the different kinds of things that you can do when you have a Bayesian metalearning algorithm. By the end of the lecture, the goal is for you to be able to understand the interpretation of metalearning within a Bayesian inference framework, and also understand the techniques for representing uncertainty over parameters and over predictions. Disclaimers, similar to the lecture on Monday, this is a very active area of research, and also like most of the class content. So there's going to be more questions than answers, and the lecture is also going to cover some of the most advanced and some of the mathiest topics of this course. I'll do my best to go slowly and hope to still be able to convey the intuition. So please ask questions throughout based on what is the content. I also see a message in the chat about being able to download the slides on the website. I reached out to a TA to do that, and so I hope that TA will upload the slides very soon. So they'll be available whenever the TA gets to it. Okay, cool. So a recap from last week. We talked about different metalearning approaches, and we specifically overviewed two different perspectives on metalearning algorithms. The first perspective was the perspective of a computation graph, and we saw how we could view different kinds of approaches within the same perspective of a computation graph that takes as input training data and a test input and processes it either with a black box function, with an optimization, or with a non-parametric computation. So this was the first perspective that we covered. And then we also thought about the algorithms from their algorithmic properties, where one property was thinking about the expressive power of the metalearner, and another property was thinking about the consistency of the metalearner. And these two properties are both quite important for a lot of applications. And there was a third property that we mentioned on Wednesday last week, where we were talking about uncertainty awareness, where we want to be able to reason about ambiguity during the learning process, which may help in a variety of situations such as active learning and reinforcement learning, and also bring in some principled probabilistic interpretations to these algorithms. And this kind of last property is exactly what we're going to be talking about today. So first, let's talk about some motivation and the benefits that this interpretation gives us. So earlier in the course, we talked about how at training and test time, we want things to match. And we also talked about how the tasks have to share some amount of structure. But we never really went into what structure means. What does it mean for tasks to share structure? What is that structure? And one way to kind of get a handle on this question is to think about that structure as a statistical dependence on some shared information, where that shared kind of information is latent. It's not something that we can directly observe. And in particular, we can consider this graphical model here, which uses plate notation, where you have some kind of shared latent information theta. There's a dependence from this shared information to each of the task parameters phi I. And I'm using the plate here to denote that there are kind of I is indexing the different the task-specific parameters for each of our tasks. And then there's also a dependence from the task-specific parameters to the labels, conditioned on the kind of inputs. So this part right here is essentially dtrain for task I, and these two variables over here correspond to dtest for task I. and J is indexing the data points within those data sets. And everything that is shaded means that it's observed. So we can always observe dtrain, but at meta test time, we can only observe X test. We can't observe Y test. That's what we're trying to predict. It's kind of partially shaded because we do get to observe Y test during the meta training process. So this is, in many ways, a graphical model that explains the kind of data generation process in a meta learning setting. And there's a couple things that you can do that this graphical model can potentially tell you about the meta learning process. So first, if you condition on the latent the latent shared information theta, then we see that the task parameters become independent. So we know that the task-specific parameters for one task and another task become independent once you condition on all of the information that they share. And second, if you don't condition on this information, then the tasks are not statistically independent. And hence, if there is shared information, then you actually have lower entropy. So essentially, when you condition on theta, that gives you more information, or hence lowers your entropy over the distribution for the task-specific parameters phi I. So basically, this equation is telling you that as you kind of condition on this shared information, you now have a better idea for what the task-specific parameters might be. They're telling you information about these task-specific parameters. Okay, so this is one of the things that this graphical model can tell us a bit about, or help us think about what's going on in this sort of meta-learning or multitask learning setting. Now, one thought exercise, if you can identify the task-specific parameter, the shared parameters theta, the shared information theta, for example, with meta-learning, in what situations should learning the task-specific parameters be faster than learning from scratch? Does anyone want to share thoughts either in chat or by raising your hand? Or any questions about what I was talking about here?
Yeah, I have one question. So here, if knowing phi I, does it mean like X train and X train Y train is independent of X I test, Y I test?
Yeah, so once you know the task-specific parameters, then the training set and the test set are independent. And this is because we assume that our training set and our test set are sampled IID. They're sampled kind of independently from the task distribution. So once you know the task, then these can be independent.
Is it like during training we infer phi I from X train Y train? At that time, it's not independent, right? I mean, when you are training the meta learning model.
Yeah, so at test time, kind of our goal is to figure out what is basically, is to kind of figure out the distribution over task-specific parameters once we have dtrain and theta. And once you're trying to kind of figure this out, it's not, well, I guess they're not independent, but still dtrain and dtest are independent. If you don't know what phi I is, then they're not independent.
Yeah.
So getting back to the thought exercise, one thought that I had in the chat is if the mutual information between theta and phi I is high, then this should be faster than learning from scratch. And so basically, I think what I'm saying is that basically if there's like a lot of shared information or a kind of pretty heavy dependence from phi I to from theta to phi I, then you would expect it to be faster than learning from scratch. And that's largely true. Any other thoughts? Okay, so one other thought here also is if you're learning from scratch, then you're basically learning from dtrain I without knowing the shared information theta. And so if all of the shared information theta, if that shared latent information tells you something about phi I that dtrain doesn't tell you, then that's a situation where we'd expect to be faster than learning from scratch, because when you're learning from scratch, you only have the training data, you don't have the shared information. So basically it's when you have high mutual information, but also when that information isn't available in the training data already. Okay, and then a second thought exercise is what happens when the entropy of this distribution right here is 0? And specifically, what happens when the entropy of this distribution is 0? It means that you can basically deterministically figure out what phi I should be if you know what theta is. And for all I would suggest that if you can basically you can deterministically figure out what phi I is for all I given theta. Yeah, and then said in the chat, this will, if this happens, then that means that the theta vector contains all of the information needed to solve the tasks. And kind of the corollary to that is if it has all the information, then you don't actually need to pay attention to detrain. And it kind of looks a bit like the memorization problem that we talked about before. And you can get basically perfect, yeah, as I said, you can get a perfect score even in the 0-shot setting, for example. Okay, so these are a couple of different kind of ways, kind of exercises or things that that are nice to look at in the, like basically kind of things that the Bayesian probabilistic modeling framework can tell you and allows you to reason about in a very formal way, which is pretty nice and gives some intuition for why you would expect metalearning to provide some benefits compared to learning from scratch, and the situations in which you would expect that to be true. So that's one motivation. And then more concretely, what information might we expect theta to contain in different situations? So say, for example, our task distribution is a family of sinusoid functions that vary in terms of the amplitude and the phase. Any thoughts on what information would be contained within theta for that family of tasks? Yeah, so said that so it kind of what theta would contain the unit sinusoid, that it would contain sinusoid functions. Do you want to give an opinion?
Yeah, I guess similar answer. Just the function itself, but things like amplitude and frequency, those can depend on phi I.
Yeah, exactly. So if different functions vary based on their amplitude and phase, then you'd expect theta to contain everything but that task-specific information. So essentially, theta will correspond to kind of that family of sinusoid functions in a way that is agnostic to the phase and the amplitude. And then when you go from kind of theta to phi I and also kind of infer phi I from data, it's going to be looking to that data to figure out what the amplitude and the phase is. Yeah, so it essentially corresponds to the general structure of sinusoid functions. Cool. Okay. Now, what about one more example? So say that we were trying to translate between different languages, and you wanted to quickly learn a model that can translate between a new language with a small amount of data. In this case, what is the information that theta might contain? Feel free to answer in chat or raise your hand. Yeah, so it said a family of language pairs, said the grammatical structures, and this is right. So basically theta will correspond to this family of language pairs. It will correspond to the shared structure among languages. It won't tell you things about like vocabulary, for example, or things that are specific to a certain language. Okay, and then it's also worth mentioning that the theta, the kind of information stored in theta is going to be narrower than the space of all possible functions. If theta was basically the space of all possible functions, then we wouldn't have any benefit from actually leveraging the information in theta to solve a new task. And now one last thought exercise is what happens if you metalearn without a lot of tasks? If you only had a small number of tasks and you ran metalearning on that, how would that affect the information in theta? So is it overfitting, which is on the right track, which is correct? Any kind of more specific thoughts on how this affects the information in theta? Yeah, so said that if you're overfitting, then theta will be too narrow. And basically kind of what can happen in this case is if you have a small set of training tasks or training functions, then you'll get this form of like meta overfitting where it considers not only the kind of not only like, for example, a family of sinusoid functions, but only the set of sinusoid functions that are in your meta training set. It's going to basically be a narrower set of tasks because it will kind of overfit to the tasks that are in the training set rather than considering the underlying distribution of functions. Okay, any questions on this before we move on to methods?
Yeah, regarding the meta overfitting, I guess maybe this point, or should I say my question is, this point maybe it's related to your use case of the overall meta-learning model, right? I mean, intuitively thinking, if your use case is generally narrower, then that means you have more like shared structures and informations in your different meta tasks, and that should increase, or at least intuitively, the performance of your model. So compared to like you have a very wide use case and you train on a very diverse set of tasks.
Yeah, so if you have a very narrow distribution of tasks, then you may not need as many samples from that distribution because you may be able to cover that distribution with a smaller number of tasks. And so if you have a small number of tasks, but your distribution is also narrow, then you may not actually see meta overfitting. It'll just be kind of fitting that more narrow distribution. Whereas if you have a very large distribution of tasks and a small number of tasks sampled from that distribution, then you're much more likely to see meta overfitting in a way that isn't actually capturing the full space of tasks.
Yeah, thanks.
Okay, I was asking, can we view meta-parameter theta as a good prior from the Bayesian perspective? And yeah, that's basically right. So you can view theta as kind of a prior over phi, and then when you're trying to estimate phi given theta in your data, you can view that as like a form of posterior inference. And then there's also a question, why everything but phase and amplitude? So phase and amplitude in this problem are the things that are task specific, and the general family of tasks is kind of the family of sinusoids for different phases and amplitude. And so theta is capturing the shared information, and the phase and the amplitude are the thing that isn't shared across tasks. Okay. Cool. So then there's our last bit of motivation. Recall that kind of so far we've been basically inferring a set of parameters phi I given a training data set and theta. And so far we've just been like learning a function that outputs phi I deterministically. It's essentially giving us a point estimate to this distribution P. And this is fine in a number of different situations, like in your homework, this was fine. But there are some situations where we may want to actually express this distribution, this full distribution, rather than only giving a point estimate of phi I. For example, if you only have a really small number of data points, then the true function may actually be ambiguous, even if you have a prior. So for example, maybe you're trying to learn a classifier between these images and these images. And the challenge is if you wanted to kind of learn a classifier, all the images on the left are people that are smiling, wearing a hat, and young, and all the people on the right are people who are not smiling, not wearing a hat, and not young. And so if you want to learn a classifier and then you're given this example of someone who's smiling and wearing a hat but not young, it's kind of ambiguous what the true answer is. You don't know if this classifier is intended to discriminate on age or discriminate on these other attributes. So in these sorts of cases where the problem is ambiguous, it would be nice to be able to represent our uncertainty about this classifier, and then as a result, be able to represent our uncertainty about this test image. Okay, another situation where we may want to be able to represent this distribution is if we want to be able to generate hypotheses about the underlying function. If we want to be able to sample from this distribution, then we need to somehow represent that distribution. And once we can generate hypotheses, then we may be able to kind of ask a user about which hypothesis is correct, for example. And if you're kind of in a safety critical setting, such as like medical imaging, for example, it's important to be able to communicate your uncertainty about the function to the user so that you can get a second opinion, for example. If you want to actively learn by actively asking for data, then this sort of uncertainty is really helpful because it tells you which data points would be helpful for learning. For example, in this kind of classification example, if you get another example of someone who's smiling, wearing a hat, and young, that's not going to be very helpful for learning your classifier. It's instead kind of labels of these data points that would be most helpful for reducing your uncertainty about the function. It's worth mentioning that there's actually a fair amount of work on active learning with metalearning. We won't go into it during the lectures in this course, but if you're interested in learning more, there's a couple of references on the slide. And lastly, this is also pretty helpful and important for learning to explore in meta reinforcement learning. And we'll talk about this a bit more in, I think in like a week and a half or 2 weeks. Okay. It looks like there's a question in the chat saying, is learning a distribution over phi I providing some sort of meta regularization? Yeah, so one of the benefits of Bayesian approaches is that they often provide some implicit forms of regularization to encourage the model to represent its uncertainty rather than overfitting to kind of a single solution that it thinks might be the right answer, but isn't quite the right answer. Is also asking, is active learning equivalent to exploration in RL? They are a little bit different from a mechanistic point of view. When you actively learn, typically it corresponds to asking for queries, like querying a user about the label for a specific data point, whereas exploration, you have a policy that is trying to collect data in the environment in a targeted way. They both correspond to kind of targeted data collection, but active learning is more often in a supervised learning context, whereas exploration is more in a reinforcement learning context where you have an agent in the environment. He's asking, is it active learning to interactive learning? Yeah, I guess active learning is the more formal term that I've heard in the machine learning community, but I think that there may be interactive learning may also be kind of a subfield of active learning. Okay, so now let's talk about some approaches for actually developing Bayesian metalearning approaches that can actually represent their uncertainty and represent these distributions. So it'll be helpful first to kind of go back to the computation graph perspective, where we can view each of these metalearning algorithms as producing a prediction over Y, given your training data set and your test input. And really the first like V0 of a Bayesian metalearning algorithm is, instead of having F deterministically output a label, have it output the parameters of a distribution over Y test, or otherwise output a distribution. This is actually technically what kind of a softmax cross-entropy loss will already do. it's already representing a softmax distribution over the discrete values. But if you do regression and use a mean squared error loss, you'll only be getting like the mean of a Gaussian distribution, and you won't be getting the variance. But anyway, you can have F output the parameters of a distribution. This can be probability values in a discrete categorical distribution. It can be the mean and variance of a Gaussian. It can be the parameters of a mixture of Gaussians. Or if you have a multidimensional y-test, then you could use an autoregressive model to kind of output a sequence of distributions where you're outputting something like P of y1 and P of y2 given y1 and so forth. And then once you output this distribution, you can optimize it with maximum likelihood. So this is pretty simple. This will give you kind of a distribution over your label for the test inputs. It's also easy to combine with a variety of methods. You just need to have the output of your model be a distribution. But it doesn't quite solve the problem that we're after. It doesn't allow you to reason about uncertainty about the underlying function. So this only gives you basically a distribution over y test given x test, d train, and theta. It doesn't, so it basically gives you this. It doesn't give you a distribution over phi I. And it'd be nice to have kind of this distribution because this allows you to think about the underlying function rather than just the individual data points. It's also limited. There's also kind of a limited class of distributions that you can represent over y-test. If you instead represent a distribution over phi I, then you may be able to get a more expressive distribution over y-test. And lastly, this kind of approach actually tends to produce poorly calibrated uncertainty estimates. Neural networks tend to overfit in some sense. This allows you to represent the uncertainty over noise in the data, but it doesn't allow you to represent uncertainty with regard to the model parameters itself. And if, for example, you give it an out-of-distribution input, then this kind of approach tends to give you uncertainty estimates that are overconfident. Okay, and then asking in the chat, is learning the distribution more difficult? Yes, in general, these Bayesian metalearning algorithms lead to a kind of a more difficult optimization process because you care not about just producing a single value of your task-specific parameters or a single output of your y. You need to actually represent that full distribution, which leads to a kind of, which makes it more challenging to optimize. Asking, can you explain the last con again? So to put it another way, there's two types of uncertainty. One type of uncertainty is what's called aleatoric uncertainty. And this is uncertainty that's inherent to the data, to noise in the data. And this kind of approach tends to be reasonable at capturing that kind of noise in the data. The other type of uncertainty is called epistemic uncertainty, which captures the uncertainty in your model itself. And this kind of approach tends to actually be quite poor at estimating the uncertainty of the model. And what I mean by uncertainty over the model is when you have kind of out of distribution data, for example, or data that's a little bit different, then your model isn't going to perform as well because it hasn't seen that kind of data. And so you want to be able to represent your uncertainty over your model parameters for those data points. And this approach tends to be actually quite ineffective at representing that form of model uncertainty. Yeah, so I think that question is, well, so asking what's the difference between inferring P of y test versus P of phi I? Can't we just infer P of y test from P of phi I? That's true. Once we have P of phi I, we can kind of sample from this distribution at the top. but we can't go the other way around. We can't figure out P of I from P of Y test. And this kind of leads to this thought exercise right here, which is that if we can do maximum likelihood training on this distribution right here, well, why can't we just do the same kind of maximum likelihood training for this latter distribution here? Any thoughts on why or why not? Basically, why or why not we can't do maximum likelihood training on this latter distribution? Yeah, so said that we don't actually know the actual phi. We don't have labels for phi I, and therefore we can't do kind of supervised training on this distribution because we don't have the labels. If we did have the labels, then we could do this, but we don't. And that's why we can only kind of do maximum likelihood training for this and not for this without introducing kind of extra assumptions or approximations. Okay, it's asking, is it required that the label Y be a distribution during a meta-train when meta-training a Bayesian model? I guess you can view point estimates as kind of approximating a Bayesian distribution. For example, if you train a model with mean squared error, you can view that as the output from the model as the mean of a Gaussian. But if you want to kind of truly represent the distributions underlying a probabilistic model, then you'll want to represent the full distribution. And then lastly, asking, does a Bayesian metalearning approach work only with optimization-based metalearning? So this version works with any kind of metalearning algorithm. You just need to have your y-test. You just need to output a distribution over y-test rather than a deterministic prediction. In the next part of the lecture, we'll talk about kind of various ways to get a distribution over phi I, both for black box methods and for optimization-based methods. Okay, great. So before we actually dive into algorithms for getting a distribution over our task-specific parameters, I want to briefly overview the kind of toolbox that we have for approaching problems in Bayesian deep learning. This is just a really broad one-slide overview that kind of will give a sense for the tools that are out there. CS330 provides a thorough treatment of this if you're interested in learning more. And of course, we don't have time to go through an entire course today. So the general goal of the toolbox is to be able to represent distributions with neural networks. And there are a variety of techniques that allow you to do this. One of the most popular techniques, and one of the most successful techniques, is to use what's called latent variable models along with variational inference. And these models try to approximate maximum likelihood training using maximum likelihood training within a latent variable model. And the way that they do this is they optimize a lower bound on the likelihood. And we'll actually get into some of the details of this method or this approach on the next slide. And what I mean by kind of a latent variable model is that you have your observed data and you have some unobserved latent variable. And this will allow you to better represent the distribution over the data itself. The second class of methods is Bayesian ensembles. This gives you a particle-based representation of a distribution that basically gives you samples from a distribution. And the way that it works is you just train separate models on different bootstraps of the data. So you basically resample the data a few times, train models on different samplings of the data. And then the different models give you basically different estimates or different samples from your distribution. So these are the kind of two of the more popular approaches and two of the more approaches that we'll talk about today. A couple other approaches. One is Bayesian neural networks, which represents a distribution over the space of parameters. And this is similar to the kind of regularization that we were talking about last time to combat memorization. Lastly, there's also normalizing flows, which allows you to represent an invertible function between a latent distribution and a data distribution, and can allow you to essentially warp things from a Gaussian distribution, for example, to a more interesting nonlinear space. Oh, and then lastly, there's also energy-based models and GANs. These estimate an unnormalized density of your distribution. And the way that they work is they tend to try to push down the data and to basically kind of represent a lower energy for the data and push up everything else. This is kind of akin to a discriminator that's trying to say like the data is good and everything else that's generated by the generator is not on the data manifold. So that's kind of a summary of the toolbox. We're really going to be focusing on the first two classes of methods today. And specifically, we'll look at how we can leverage these first two in the context of metalearning. The others could also be useful in developing new methods. Any questions about this kind of one-slide overview of Bayesian deep learning? Okay. So we're first going to look at how variational methods can, variational latent variable models can allow us to build a Bayesian metalearning method. And so I'd like to give some background on how these methods work. And in particular, in a simplified setting where we have just kind of a set of data points X, maybe of n of those data points, we assume that we have kind of this latent variable Z that underlies our data, and our goal is going to be to represent a distribution over X. And we want to represent a expressive distribution because maybe X is images or X is language, and we want to be able to capture something that's more complex than like a Gaussian distribution over images, for example. So X is the observed variable, and Z is the latent variable. And then essentially what variational gives us is the evidence lower bound that basically tells us that the likelihood of our data is lower bounded by this expression right here, which is basically the samples from this variational distribution Q. Well, an expectation over samples from this variational distribution of the log probability of the joint plus the entropy of our variational distribution. And perhaps the more common way to write this is something that looks like the kind of likelihood of samples decoded from our latent space minus the KL divergence between our variational distribution and our prior over Z. So before I go forward, I guess I'm curious for how many people would it be helpful if I actually kind of derived this bound on a whiteboard-like thing. So maybe maybe say yes if that would be helpful, and no if you think that that would not be helpful. Okay, it looks like from the chat and from the yes answers in the participants list that it would be helpful. So let's go through that. Cool. So we want to do maximum likelihood trading, and specifically we want to be able to maximize the log probability of our data. The probability of our data is going to be P of X. And we're going to model P of X, this distribution, with this latent, by introducing a latent variable. And so we can view this quantity as the log of this integral, where we're basically going to be introducing this latent variable Z and then integrating it out and then taking the log. So this is the introduction of the latent variable. Now, what this kind of, what variational inference intends to do is to introduce what's called the variational distribution. I'll denote it as Q of Z. And the goal of Q of Z is going to aim to try to help us estimate the bound on our likelihood. And Q of Z, this can really be anything. It has to, you don't want it to be, it has to be a proper distribution, of course, but as you can see in this equation, it doesn't really matter exactly what it is. There are some choices of Q that will lead to a better estimate. Often in practice, you actually have a variational distribution that is conditioned on your data point. This will kind of allow you to get a better estimate of Z for a certain data point. But in practice, you can actually really choose whatever you want to be on the right-hand side of the conditioning bar. Okay, so this is still an equality so far. And what you can do is you can move this Q over here, and that gives you an expectation. So this equals the log of the expectation under Q of P of X comma Z divided by Q of Z dz. So we're still at equality here. And then, and this is nice because now we no longer have to compute this integral over Z. We can essentially approximate this now by just drawing samples from Q of Z. Now here's where the bound is going to come in. So we want to be able to estimate this by drawing samples from Q of Z. But of course, because we have this log here, that's a bit annoying because the expectation over Q isn't on the outside. And so like was mentioned in the chat, we can apply Jensen's inequality and basically bring the log inside the expectation. And I'll actually write this out a little bit more, and we get something that looks like this when we bring the log inside the expectation. Also, I realized I shouldn't have a dz here. Okay. And then when we kind of write this out in terms of the first expression that was on the slide, we get something that looks like expectation under Q of Z of log P of X comma Z plus the entropy of Q. And this is basically what was written on the slide. So the reason why you may want to do this is that this is something that we can optimize. And in particular, if you set Q, if for example you set Q of Z given X to be a Gaussian distribution, then you can represent this in closed form, and this is equal to log of P of X given Z time plus log of P of Z. We often set P of Z to be like a normal Gaussian distribution, and this is represented by a neural network. So this may have parameters theta. Oftentimes you have the variational distribution have parameters phi. And you optimize basically, when you take a maximum over this, you also take a max over this, both with respect to phi and with respect to theta. Okay, so this is how we get this kind of lower bound on the likelihood of our data. And you can see that the term that I just wrote out is the same as what's written right here, where you basically get the likelihood after drawing samples from Q plus the entropy of Q. Intuitively, you could also view this as something that's trying to make Q of Z match P of Z. and then also maximizing the likelihood of P of X given Z when you're sampling from Q of Z. Okay, a couple more things to mention. So P is the model here. P of X given Z is represented with a neural network. P of Z is represented with just some normal distribution. The reason why you represent it as this is that the next layer of P of Z can transform it into something that's more interesting than that. So it doesn't actually really matter. This can be really any simple distribution. And then Q of Z given X is often called the inference network or the variational distribution. You can think of it as something that is kind of trying to infer the posterior over Z given your data point. And again, really, like Q can be whatever you want, but it's helpful to optimize it with respect to your bound. And basically, if you maximize your bound, then you'll make both with respect to P and with respect to Q, then you'll make it tighter. So that's why you want to kind of, optimize both Q and P. Your model parameter is theta, your variational parameters are phi. So any questions on this so far? Okay, now one problem that comes up is you need to backpropagate through sampling. So when you note that basically both of these terms depend on Q in the expectation, and we actually need to backpropagate into the parameters of Q when we optimize this. And so that means that we need to, if we want to optimize Q, we need to backpropagate through this sampling process and compute the derivative of the expectation of Q with respect to Q. And so the reparameterization trick is kind of what allows you to fix this problem. So if you set Q to be a Gaussian distribution, not only is it easy to compute this KL divergence or equivalently this entropy, if you have a Gaussian Q, then you can set Q to be equal to the mean of Q plus the standard deviation times some noise, where noise is just drawn from this like standard Gaussian distribution. And note that this function is differentiable with respect to the mean and variance. And so you can essentially reparameterize this distribution in terms of this standard normal distribution and get something that is differentiable with respect to the mean and the variance, and basically directly backpropagate into the mean and variance of the distribution, which is pretty cool. Okay. There are a couple of questions in the chat. So one question is, how will we leverage the variational model to do supervised learning tasks? I'll get into this in a second, but kind of the sneak peek into what it will look like is you can think of the latent variable. Well, I guess there's different ways to view it, but you can think in a meta-learning model, phi I becomes a latent variable, and your data becomes like dtrain becomes your observed data. And so this framework will allow us to do inference over our latent variable. Is asking, can you explain the difference between model parameters and variational parameters? So the model parameters, I guess there's a few different ways to view it. One is kind of mechanistic and one is more theoretical, but I guess from a mechanistic standpoint, you can view the model parameters as representing basically our model, basically modeling P of Z and P of X given Z. And when we want to sample from this model, we only use the parameters of our model here. The variational parameters are what allow us to kind of better compute this lower bound on our likelihood. And they're used during training, but they aren't at all used during testing if you want to sample from this model. So that's kind of what they are from a mechanistic point of view. And I guess also from a conceptual point of view. Okay. Oh, and then lastly, this is called amortized variational inference because this inference network Q is doing what's called amortized inference because instead of trying to optimize over Z for each example, you're just trying to estimate it by training a model that kind of estimates it for you. So how might we do metalearning leveraging these techniques? So we can consider a setting where we have kind of a black box neural network that takes as input a training data set and outputs a distribution over Q of phi. And then we use phi to make predictions. Now in the standard VAE, we can view the observed variable as x, the latent variable z, and we can derive a lower bound. Now in the metalearning setting, we now have an observed variable that's our data and the latent variable, which is our task parameters. It's kind of an analogy that you can make to the standard variational autoencoder. And you can also use this to derive a lower bound on the likelihood of your data that looks something like this. That's basically just analogous to the lower bound of the VAE, where you have some kind of inference network over phi. You maximize the likelihood of your data given phi, and then also minimize the KL divergence between your inference network and your prior over your parameters. What should Q condition on? So in the VAE setting, Q conditioned on X. In this setting, we're going to be conditioning Q on our training data. So we're basically going to be doing kind of approximate inference to infer our task-specific parameters given our training data. This inference network is going to look a lot like the black box metalearner. This equation just kind of replaces the probability of the data given phi is just the probability of the labels given x test and phi. And then lastly, where do the meta parameters come in? The meta parameters will be part of the model. So whenever we try to estimate phi, we'll condition that prediction on theta, on our meta parameters. So theta here again is the parameters of this neural network. So this is like f theta, for example. Okay, do you have a question?
Is the f theta the encoder of the VAE here?
So yes, well, so the encoder, I guess the this is equivalent to the encoder or the inference network in a VAE.
Yeah.
That's basically you can view as analogous to the f theta right here.
Okay. So basically, theta is learned as another network because input will be d-train and theta, and then we are getting phi out of it, which is a z parameter, right?
Yeah, so it's basically this inference network right here.
Okay.
You could also condition on theta here. This is kind of analogous to like a model that doesn't output all of the parameters; it just outputs a subset of the parameters. This just changes your graphical model a little bit if you condition on theta here, such that you get something that looks more like theta phi I, and then when you make predictions for y, you get something that looks also like this, for example, in your graphical model.
So here I mean in this network, we are giving input theta and d-train and then infer phi, and then it goes from there.
Yep. Yeah, so you basically have your inference network that infers the task-specific parameters given your data and your meta parameters. You maximize the likelihood of the kind of labels under your task-specific parameters, and then you additionally have this KL term that encourages this, basically encourages this inference network to produce a proper distribution over phi.
Is the theta is represented as a neural network or some other distribution? Like we are also learning theta, right? I mean, it's not like we knew theta to start with.
yeah, you're also, theta is being optimized here. Okay, so the final objective is here for completeness. It's asking how many samples do you use for training. In a VAE and in this setting, it's actually often fine in practice to just sample once from this distribution, although you'll get kind of a tighter estimate of your likelihood if you sample multiple times. Okay, so this is one way to produce a Bayesian metalearning algorithm that allows you to get a distribution over your task-specific parameters given your training data. And this allows you to get non-Gaussian distributions over y-test. You don't actually have to, you're never actually explicitly representing the kind of distribution of y-test given x-test, d-train, and theta. Instead, what you're doing is you're first representing p of phi, and then you're representing p of y-test given x-test and phi. And because you don't actually have to explicitly represent this, that makes it easier to represent more complex distributions. It also produces a distribution over functions. It allows you to produce a distribution over kind of task-specific parameters phi. The downsides is that you can only represent Gaussian distributions over p of phi I. This is important so that you can calculate the KL and so that you can use the reparameterization trick. This is kind of more of a, it limits the expressivity of this distribution. In practice, Gaussian distributions over parameters are fairly effective for representing distributions because your parameters will be transformed in a nonlinear way to produce predictions. Okay, so that's kind of a way to use variational inference to develop a Bayesian black box metalearning techniques. Is asking we can do a mixture of Gaussians too, right? There is a way to approximate the KL, but it's difficult to do the reparameterization trick with a mixture of Gaussians. There are some methods that try to approximate it though. And then it's asking for non-Gaussian, can we not estimate KL using Monte Carlo samples? So you can estimate the KL. It's more difficult to backpropagate through those that sampling process, which essentially basically like this reparameterization trick right here. This is really easy to do for Gaussians. It's a lot harder to do for non-Gaussians. But if you're interested in this, there are methods that try to extend variational autoencoders to other distributions over your latent variable. But really the de facto thing to do is to use a Gaussian distribution. Okay, so that was a black box method that was kind of using a neural network to produce a distribution over phi I. What about some optimization-based methods? So the first thing worth mentioning is this paper here that actually cast actually the kind of original deterministic mammal algorithm as a Bayesian method, very approximately. And the way that this works is we basically have the same graphical model as before. It's just written a little bit differently where we're not writing out the train and the test set separately. And if we're trying to maximize, if we want to kind of do maximum likelihood in this model, we're maximizing the likelihood of the data given our metaparameters. We can expand this out by introducing the latent variable phi I in here, and then integrate out phi I. And what this paper did is, let's say, they said that, well, what if we very crudely approximate this integral by the map estimate? Basically, the value of phi I that has the highest likelihood. This is a very crude approximation to the integral, but if you have a very peaky distribution, it may be not that crude. But in any case, it's a fairly crude approximation. But under this crude approximation, you can show that you can essentially show that mammal corresponds to doing inference in this graphical model because of this prior result here. This prior result said that gradient descent with early stopping corresponds to map inference under a Gaussian prior with the mean at the initial parameters. And this was exact in the linear case and approximate in the nonlinear case. So essentially by making this crude approximation and by also making this approximation here in the nonlinear case, this essentially provides a Bayesian interpretation of MAML, where you can view MAML as providing this map estimate, using that map estimate to estimate this integral, and therefore kind of showing a correspondence between the MAML algorithm and this graphical model here. Of course, this is all kind of very crude, and also under this interpretation, we still can't sample from this distribution here. So it's not very useful from the Bayesian, from the kind of standpoint of representing distributions. So there's a few different things that you can do about this. One thing you could do is recall the black box metalearning approach that we just talked about. And remember that this kind of inference network, this variational distribution can really be any arbitrary function. So from this standpoint, you could just put a gradient operator inside Q and then kind of have it correspond to an optimization. And so this is kind of what this paper by Ravi and Beetson did, where Q basically corresponded to running SGD on the mean invariance of neural network weights with respect to your training data. And basically uses all the machinery. They still optimize this objective, they just change the form of Q. And the benefit of this is that it does give you a way to run gradient descent at test time while still giving you a distribution. Again, here, phi given theta is going to be modeled as Gaussian, which may have its downsides. Okay, so this is the first way that we could use it, kind of introduce a Bayesian optimization-based metalearning algorithm. What about a non-Gaussian posterior? So the kind of simplest thing that we could do is to just do ensembles. Basically the technique where you train multiple different neural networks on different subsamples of the data. And so really the simplest thing that you could do is to train an ensemble of mammals where you just train M independent mammal models. And you get something that looks like this. And note that you can also use ensembles with black box and non-parametric methods as well. This actually works pretty well, but it won't work well if your ensemble members are too similar to one another. And this paper by Kim et al. Proposed to use what's called Stein variational gradient to actually optimize for a more diverse set of ensemble elements, which basically just tries to push different ensemble particles away from one another to get a more diverse ensemble of mammals. And as a result, optimize for a distribution of particles that produce a high likelihood. The benefit of this is that it's simple and it tends to work well. It also gives you a non-Gaussian distribution, which is nice. The downside of this is that it tends to be pretty expensive because you have to train complete M different model instances, which may be a lot of computation and memory, which is actually exactly what was brought up in the chat. You could just kind of do this just on the last layer only, which will be a little bit cheaper. But then you only get a distribution over that last layer, which may be a little bit less expressive. There's a question in chat about how large is M. I can't remember exactly how many they used in this paper. It's common to use something like 3 to 5 so that your computation doesn't blow up too much. Do you have a question?
Yeah, I meant to ask, like, for these mammals, like different mammal models. So does it matter if these models are trained on the same data or like different subsamples of data and bootstrap then after?
Yeah, this is a good question. So if you use different bootstraps of your data, then it has a proper interpretation as representing a distribution. in practice, people often ignore that and just train different models with a different initialization and a different order of mini batches. And that often leads to ensembles that work just as well as using different samples of your data. Yeah, so in practice, you can often kind of skip the subsampling part and just change the initialization and change the order of the mini batches. If you want something with a theoretical kind of backing behind it, then using different bootstraps is the more correct thing to do. Okay. Then lastly, I want to talk briefly about whether we can model non-Gaussian posterior over all parameters. And we want to think about sampling parameter vectors with a procedure like Monte Carlo. One more question actually from on the last slide. Are they trained independently, or like each iteration average loss from each model is used to update the weight? They tend to be trained independently. Okay, so this last method that we'll talk about, the intuition behind it is that it's trying to learn a prior over our parameters, where a kick in any direction can put us into different modes of that function. Essentially something where we're like, maybe this is one mode of the function that we want to learn, where we have a classifier that's along the lines of like, that discriminates on the means of just smiling and young, one classifier that discriminates on smiling and wearing a hat. And we want a prior here such that if you add a little bit of noise from this starting point, you end up in one of these two modes. And then if you run gradient descent, you'll end up at the kind of optimum for each of those two modes. I just put down two modes here because it's easiest to visualize that, but in practice you may have more than two modes. We're a bit low on time, so I might kind of go through this quickly. The goal is we're going to be representing both a distribution over theta and a distribution over phi given theta. And our goal is to be able to sample from phi given our data. This is independent of X test, so you can, once you condition on X train and Y train, you basically get this independence. This is, if we want to be able to approximate this, you get this kind of pretty intractable integral over all possible parameters theta, which is not something that we want to try to approximate. And kind of the intuition behind this approach is that if we knew P of phi given theta, X train and Y train for a single sample from P of theta, then things get a lot easier. So if we knew what this was, then we can just use ancestral sampling to first sample from P of theta, and then sample from this distribution. So the way this works is we can basically, like the Bayesian interpretation of mammal, very crudely approximate this as the map estimate of phi, which is similar to running gradient descent, and then do training on the full thing with amortized variational inference. So kind of, I guess the most important thing though is what happens at test time. Meta training gives you a parameter, a distribution over theta, and what this corresponds to is basically taking the mean of this distribution, adding sampling from theta, which corresponds to adding noise to the mean in correspondence to the variance, and then running gradient descent, which approximately corresponds to sampling from P of phi I. And this is something that gives you a kind of non-Gaussian posterior over phi. It's also pretty simple at test time and doesn't have to be trained with an ensemble, for example. The downside is that it involves a more complex training procedure that I didn't have kind of time to go through in detail. Okay, so to summarize the methods, V0 is just outputting a distribution over Y test, which is simple. but can't reason about uncertainty over the underlying function. We then talked about black box approaches that can use variational inference to represent a distribution over a latent variable. This can represent non-Gaussian distributions, but it can only represent Gaussian distributions over phi I. And then we also talked about optimization-based approaches where you could use amortized inference, ensembles, or a hybrid inference procedure, and they each have their own pros and cons. The first two are pretty simple, but have kind of various downsides, such as being a Gaussian posterior over phi, or having to maintain M model instances. The last one is more complex, but it does give you a non-Gaussian posterior. Okay, so this is kind of a summary of the methods. One thing that I'd like to go over at the end and wanted to make sure I have time for is to talk about what you can do when you have these Bayesian Metalearning methods and how do you actually evaluate a Bayesian Metalearning method. So one thing you could do is use a standard benchmark like Mini ImageNet. And this is nice in that it's standardized, it has real images, it's a good check that the approach didn't break anything. But the downside is that metrics like accuracy don't actually measure whether your uncertainty is accurate. And the task may not exhibit any ambiguity. Representing uncertainty may not actually be beneficial in these circumstances. So what I want to talk about briefly is what are some better problems and metrics for evaluating these kinds of methods. And it really depends on the problem that you care about. So one thing that you could do is look at kind of some toy 2D problems that allow you to visualize things very easily and specifically design them to have ambiguity. So for example, you could train a model on both linear functions and sinusoid functions, add some noise to the data points, which are shown in purple, such that in some cases it's ambiguous whether it's a sinusoid function or a linear function. And then you could visualize the different kind of functions that are predicted by the model and see that it can actually represent a distribution over those functions. So for example, in this case, because all the data points are up here, it's unclear exactly kind of which line is the true line of the function. And in this case, because the data points are here and up here, and because there's noise in the data, it's unclear if the function is a sinusoid or a linear function. You can also design an ambiguous classification problem where there's all of the problems in the data distribution have circular decision boundaries, but you only give it one data point to infer the function from. And when you do that, if you only give it this green plus, for example, then it's ambiguous where exactly the decision boundary lies, and you can actually visualize the different functions. You can visualize basically the different functions that it's estimating based off of this single data point. So this is one example of how you can visualize and measure whether or not the uncertainty in the model is accurate. But of course, these are toy problems that may not translate to more complex problems. Another thing you could do is take a more ambiguous problem. For example, this paper looked at the problem of being able to generate images given just one view. So for example, it's given this view, and it's ambiguous because there are parts of the image that are occluded, so it doesn't know what the object will look like when it's flipped around 180 degrees. And by representing uncertainty with like the Versa approach, which is a method actually similar to one of the things that we talked about today, it can represent this uncertainty in a much more crisp way than a more naive approach. And this also leads to kind of better reconstruction accuracy because this is an ambiguous few-shot learning problem. Another thing that you could do to evaluate these methods is look at kind of mode coverage and likelihood on ambiguous tasks. So you could consider the set of ambiguous classification tasks that I talked about at the beginning, and then evaluate if you give it something ambiguous where 3 of the attributes are shared between the positive and negative examples, and there are 3 potential modes that share different numbers of attributes, then you could see like whether it's able to cover all 3 of these modes, or basically how many modes the distribution will capture when you sample from it, And you can also measure the log likelihood of this. And then lastly, one thing you could do is look at what's called a reliability diagram. And this is basically trying to see that for data points that are more accurate, for data points that it makes accurate predictions on, is it confident in those? And for data points that it is less accurate on, is it less confident in those? So this is plotting the confidence of that the classifier produces versus the accuracy. And if you basically see that the red bars follow this line, that suggests that the confidence is calibrated to the true accuracy. Whereas if you look at kind of standard mammal, for example, it's not very calibrated, and it doesn't, there's kind of a difference between this line and where the bars are. Okay. Oh, and then lastly, and actually the kind of most interesting thing that you could do is actually evaluate whether it's useful for active learning. So you can basically say, if I give it 1 or 2 or 3 or 5 additional data points, can it select data points that lead to kind of lower and lower error compared to just randomly selecting data points? So in both of these two experiments, they sequentially choose a data point, and they choose the data point with the highest with the highest predictive entropy, basically the highest uncertainty to be labeled, versus just choosing a random data point. And you see that you can basically get a more accurate classifier faster with fewer labels by leveraging this uncertainty. So I was asking, can we use a simple approach like mean field approximation for variational inference? Will it work well? So these methods are actually already doing something like mean field approximation, where the distribution over the latent variable is kind of an independent Gaussian distribution. So it's basically assuming that each of the dimensions in your latent variable are independent from one another.
Yeah, so in this VAE kind of approximation, can we use like a flow in the latent space to make it non-Gaussian? That we can still compute it, right?
Yeah, so you could definitely use something like normalizing flows to get a non-Gaussian distribution. There may be works that do something like that, but I don't know of any off the top of my head.
Is it like a benefit of doing like addition, like why we want to do it? Because is it like most cases a simple Gaussian might work, but when we adding normalizing flow, it means we are having a better title bound. Does it mean that the uncertainty will go down? Is like may or may not be fair? Because they're making the complex model said there must be some benefit of adding it. Otherwise, why should we?
Yeah, so my intuition is that if you can represent a non-Gaussian distribution, you'll give more flexibility to the meta-learning process. And with more flexibility, you'll be able to fit the meta-training data better. That's a hypothesis. It's not, I mean, perhaps there are cases where a Gaussian distribution is kind of flexible enough. It also seems, I guess, using non-Gaussian distributions also, I guess, placing a Gaussian distribution seemed like a pretty restrictive constraint on the distribution that you can represent. So my guess is that you would be able to better fit the data with a non-Gaussian distribution, but, and it just kind of seems aesthetically more appealing, but I haven't verified this myself.
It depends on the training and the tuning, because just having a high likelihood doesn't really mean that I'll get a better learning. But yeah, I agree. Like having a non-Gaussian by adding flow will probably get a better capturing the distribution of different things, but not Gaussian anymore. But yeah, I agree. And can we also like instead of like we did like VAE kind of to learn the representation, like is it like a flow based is also possible? Like if you want to learn directly this phi are using flow, because I can still learn a distribution in it, like autoregressive flow kind of techniques, right?
Yeah, so you can't train like the flow model directly on the parameters itself because you don't have supervision on the parameters. But you can basically, if you use it to represent a distribution and then use that, you use that model to make predictions on the data points, then you should be able to backpropagate into the model, into your normalizing flow model.
One last question. So last week we had this post prediction problem where we had this regularization kind of the information flow. So if we take the same thing in a variational or a Bayesian model directly, does it supposed to have better regularization here? Like it's not gonna, or like as good as like if we just use this kind of a information flow regularization. Because here we're also learning a distribution of 3 to 5.
Yeah. So almost all the works that I talked about today preceded the work that we did on memorization. So that wasn't something that we had really an idea or a notion that we had formalized when we were working on these Bayesian Metalearning methods and when other people were working on them. I do think that in principle, these methods should be more robust to memorization, but it's kind of a very active area and not something that I've seen from these works yet.
Be a good project idea, like to look at this kind of a Bayesian approaches to like this kind of more complex post prediction kind of problems, like see if it's equally good or like a different kind.
Yeah, I think that it could be reasonable to explore whether these Bayesian metalearning methods prevent memorization. What's your question?
I actually have 2 questions. So the first one is very naive. So it's about the ensemble approach. So say if we only have 5 mammals in the ensemble, so how can we make any accurate prediction for the distributions of the parameters?
So it really depends on what you're using the ensemble for. People typically use ensembles to get a rough estimate for uncertainty, and the way that you can do that with an ensemble is to look at how much the ensemble elements disagree with one another. And empirically, people have found that you only need like a few ensembles to be able to get a reasonable estimate of that sort of disagreement. But yeah, it is a little bit strange that you wouldn't need more than that per se to get a good estimate. That's kind of what people have observed in practice.
Yeah, so I have another question. So kind of today, what the Bayesian models you're talking about, kind of to capture the uncertainty in the models. So you also mentioned that there are also uncertainties in the data. So I'm wondering if we know some of the uncertainties in the data, how can we leverage these properties of the data?
Yeah, so a lot of these methods that can capture model uncertainty will also be able to capture uncertainty in the data as well. Capturing data uncertainty in the data is like the easier kind of uncertainty, essentially, compared to capturing uncertainty in the model, because it when you kind of train a distribution to the data, it will, it should represent that fairly readily.
So, I mean, if we explicitly know the uncertainties in the data, for example, we know when we take an image, we know, for example, how the noises are distributed in this image. Can we use this kind of information?
If you have knowledge of the noise in your data, then you could definitely leverage that by augmenting your kind of output distribution. Typically, when I say noise in the data, I mean more like noise in kind of P of y given x, because this is what you're predicting. Mm-hmm. So if you know the distribution of noise in your labels, then you could basically like tack that noise model onto the output of your neural network. In practice, that sort of noise isn't that hard to learn though either.
I see. Thank you so much.
Hi. So yeah, the noise in the data. So version 0 was, I think, which you mentioned, is a noise in the data. And then the rest of the thing is like uncertainty over the model parameters, right? So in the last part of the lecture, when you were talking about the evaluation and you brought up like the reliability diagram plots, wouldn't just the uncertainty on data show me this? Like I'm trying to figure out how I would interpret uncertainty in the model with this. Like wouldn't if I just did uncertainty over my data and I did these plots, I could gather, right? Like my accuracy is higher than.
Yeah, so it depends on your test data. If your test data is out of distribution a little bit, then you may be like inaccurate on that data, but overconfident if you don't measure your model uncertainty. If your data is, if the data that you're evaluating this is very much in distribution, like if you evaluate this on your training data, then that would be kind of what you're saying. It'd be just looking at the data uncertainty.
I see. So then what you're suggesting is in this reliability diagrams on the confidence part, one should do just uncertainty over the model parameters, right? For the confidence.
Well, so the confidence score, I guess, I can't remember exactly how they were measuring this in their method, but yeah, you basically want this to plot this confidence in terms of the the variance in the predictions that the model is making, essentially. And if it is accurately representing model uncertainty, then you would expect this to be more calibrated or more correct, especially for data that's a little bit out of distribution. Does that answer your question?
Yeah, thanks.
Okay, sounds good. I'll see everyone next week.